All right, welcome to the Explainer. Today, we're going to tackle a really powerful mathematical tool, one that's absolutely essential for engineers and physicists, the Laplace Transform. Now, I know it sounds complicated, but trust me, at its heart, it's just a brilliant shortcut.
So to get our heads around this idea of a transform, let's think about something you probably already know: logarithms. Logarithms are themselves a type of transformation. They take a really difficult operation, like multiplying two massive numbers, and they turn it into a much, much simpler one, just adding them together. It's a classic mathematical shortcut.
Okay, so that gets you thinking, right? What if we could pull off the same trick for calculus? What if there was a way to take these complex, messy differential equations, the things that describe everything from electrical circuits to vibrating springs, and transform them into something way, way easier to solve?
Well, that is exactly what the Laplace transform was designed to do. So here's our roadmap for today. We're going to start with why this shortcut is so useful. Then we'll look at how the transform is actually defined. We'll open up the toolkit of properties and common functions. Then we'll figure out how to work backwards to get our final answer. And finally, we'll put it all together to solve a real differential equation. All right, first up, let's get right into why this thing is such a game changer, how it turns calculus into simple algebra. So here's the big idea, the whole reason this thing exists. It's a translator. It takes the gnarly, often intimidating language of calculus, with all its derivatives and integrals, and it translates it into the comfortable, familiar world of algebra. That's the core magic trick right there.
Okay, so how does this magic trick actually work? Let's take a quick peek under the hood at the mathematical engine that drives this whole thing.
Whoa. Okay, I know what you're thinking. That integral looks a little intense. But don't worry, you almost never have to solve this by hand. The key thing to understand here is what it does. It takes a function of time, our f of t, and it churns out a totally new function, f of s. This new variable s, you can think of it as a complex frequency. We're basically shifting our perspective from how does the system behave over time to what are the fundamental frequencies and decay rates that make up the system's behavior. And this move is what makes everything possible. We are literally jumping from one universe to another. We start in the time domain, the world we all live in, where things happen over time. But then we leap into this new place, the S domain. And why would we do that? Because in the S domain, the rules are different. The really hard calculus problems from our world, they become simple algebra problems in this new one. Now here is the absolute best part. You don't have to wrestle with that big, ugly integral every single time you want to use this. Nope, we get to stand on the shoulders of giants. We have a whole toolkit of pre-solved transforms and powerful properties that do all the heavy lifting for us. Now, there are a few really useful properties here. But honestly, the one you see on that second line, that's the superstar. That's the main event. Just look at it. Taking a derivative in the time domain, which is a calculus operation, becomes just multiplying by s in the s domain. That's it. That is the secret sauce. That one property is the engine that converts calculus into algebra. And this is basically our translation dictionary. Think of it as a cheat sheet. For pretty much any basic function you can imagine, a constant value, an exponential curve, a sine or cosine wave, someone somewhere has already done the hard work. They've figured out the Laplace transform. All we have to do is just look it up in a table, just like this one. No fuss. Okay, great. So we've jumped to the S domain, we've used our simple algebra skills, and we've got an answer. But what good is an answer in the S domain? We don't live there. We need to bring our solution back to the real world, back to the time domain where it actually means something. And for that, we have, you guessed it, the inverse Laplace transform. It does exactly what it says on the tin. It's our undo button. It takes our algebraic solution, our f of s, and translates it right back into the time domain function, f of t, that we were looking for all along. So, I want you to picture this whole workflow as a round trip. You start with a hard problem here in the t world. You pack your bags, take the Laplace transform over to the s world, where the problem is way easier. You solve it there using algebra, and then you take the inverse transform to come right back home with the solution in your hand. Okay, theory time is over. Let's see this thing in action. We're going to walk through how you actually use this process to solve a real differential equation step by step. The entire method really just boils down to a simple 3-step mantra. Just remember this. 1. Transform. 2. Solve. 3. Inverse transform. That's it. You transform the entire equation into the S domain, you solve the new algebraic equation for your f of s, and then you take the inverse to get your final answer. Transform, solve, inverse transform. Okay, but there is a little wrinkle here.
In step 2, when you solve for f of s, you often end up with a big, messy algebraic fraction. And when you look at your cheat sheet, it's not going to be on there. So how do you take the inverse of something that's not on your list? Well, we need one more tool from our algebra toolbox. It's a technique called partial fraction expansion. What this technique does is actually pretty clever. It lets us take a really complicated, scary-looking fraction, like the one you see here, and break it apart into a sum of much simpler, bite-sized pieces. And the magic is that each of those simple little pieces is on our cheat sheet, so we can find the inverse for each part individually and then just add the results back together. It turns one impossible problem into 3 easy ones. Let's make this real. On the left, you see a classic differential equation. It's got second derivatives, first derivatives. It's a calculus problem through and through. But look what happens after we hit it with a Laplace transform. On the right, all those derivatives are gone. They've just been replaced by multiplication with s. All that's left is an algebra problem. A slightly messy one, sure, but it's just algebra. We just need to solve for that x bar. And so, after you do that algebra, after you use partial fractions to break up the messy result, and after you look up the inverse for each simple piece from your table, you get this, the final answer, a function of time, x of t, that perfectly solves that original tough-as-nails differential equation. And this quote really just nails it. The true genius of the Laplace transform isn't that it lets you solve new problems you couldn't solve before. It's that it gives you a systematic, repeatable, almost mechanical way to do it. It provides a roadmap to turn the twists and turns of calculus into the straight, simple lines of algebra. And look, this is not just some neat math trick for a textbook. This is the bedrock of modern engineering. It's happening inside the control systems that fly airplanes. It's used to analyze the circuits in your smartphone. It's fundamental to signal processing. It is a key that unlocks our ability to understand and predict how complex systems change over time. So the real question is, now that we have this powerful tool to turn complexity into simplicity, what other challenging